Welcome to this video presentation on stronger three-sum lower bounds for approximate distance oracles via additive combinatorics. My name is Nick, and this is joint work with Amir, Abboud, and Karl Bringmann. Before we start, let me mention that actually, after we submitted this, we learned that there is another team of researchers that had apparently worked on the same problem, and they scored almost the same results with almost the same techniques. So credit also goes to Zejin and Yinzhang Su, with whom we will actually share a session this year at STOC. Okay, so let me start by explaining what is a distance oracle. Imagine the following situation. You're working with a graph. You're particularly interested in the distances in the graph, but maybe it is too expensive to compute the distances from scratch whenever you are interested in the specific distance between two vertices. So a very natural approach is to pre-process the whole graph and then to support queries which return the distance between a given pair of nodes. This is what we call a distance oracle. Now, it's also very natural that instead of demanding an exact answer, you are typically interested in, well, an approximate answer to the distance. So we allow that the answer is off by a small multiplicative error, to which we will usually refer as the stretch. Here's an example. Suppose that in this given graph, which is undirected and unweighted, by the way, we have pre-processed it with a distance oracle, and then this query comes in. Well, as you can see, the distance between these two nodes is 2 in the graph. However, the distance oracle is not required to report 2. Say if it has stretch 2, it could as well report that the distance is approximately 4, right? Which is only off by a factor of 2. So for instance, if you think about the data structure point of view, maybe the distance oracle forgets about this path and instead just remembers this one. Okay, so what's the state of the art? On the left, I'm going to show you the upper bounds, which are known, on the right, the lower bounds. And actually, in terms of the upper bounds, there is this one amazing result from almost 20 years back by Thorup and Zwick, who proved that there is a whole family of distance oracles. So specifically for any integer k, there is a distance oracle with stretch 2k minus 1, free processing time order of m times n to the 1 over k, and constant query time. These running times are actually very natural. And well, it seemed tough to improve upon this. And well, despite 20 years, despite this result happening 20 years ago, most of the improvements are only for special cases. So for instance, if the stretch is very small, or k is super constant, or the graphs are particularly dense, and so on. So in its full generality, Thorup-Zwick actually remains the state of the art. So it's a very natural question to ask, is this optimal? Is there a way to improve upon Thorup and Zwick distance oracles? Very specifically, let's suppose we insist on the running times of Thorup and Zwick. Then the question would be, what is the best stretch, let me denote by f of k, that we can achieve with pre-processing time of m times n to the 1 over k, and well, almost constant query time. And this is the question which we will study in this paper. Okay, so what is known towards this? Are there some lower bounds? And it turns out if you talk to researchers, many will actually tell you, yeah, that this is solved, right? There is this girth conjecture by Erdős. And so the girth conjecture, it states that there are graphs with girth 2k plus 1 and roughly n to the 1 plus 1 over k edges. Now, this as a consequence actually has that if you take one of those graphs, you pre-process it by the distance oracle, you cannot afford, by a distance oracle with stretch strictly less than 2k plus 1, you cannot afford to forget about any of the edges in the graph. Any of the edges would lead to a much higher distance estimate than you're allowed with the distance oracle. So actually, your distance oracle needs space n to the 1 plus 1 over k. And as it turns out, this actually proves, assuming the girth conjecture, that Thorup-Zwick distance oracles are space optimal. However, it doesn't have any implications on our driving question on the value of f of k. Specifically, think about sparse graphs, about graphs where the number of edges is roughly equal to the number of vertices. And for those graphs, the girth conjecture is essentially meaningless because it postulates the existence of a denser graph. Okay, so what else is there? Turns out that by my two co-authors and also by Sarah Khoury and Amir, 1 year ago at STOC, they could prove that f of k scales linearly with k. So specifically that f of k is at least k by 6.37. This number, it depends on the matrix multiplication constant, which is why it's a little bit weird. Unless either the threesome conjecture or the APSP conjecture from fine-grained complexity theory fails. So this is an amazing step. It proves that actually the Thorpe-Zwick distance oracle plays in the right order of magnitude. The stretch, they recall that they have stretched 2k roughly. It has to scale linearly with k. So all what remains is to nail down the right constant. And in this work, we make significant progress towards this question. So our main result is actually that f of k is at least linear in k, at least k plus k up to lower order factors, unless the threesome conjecture from fine-grained complexity theory fails. Now, unfortunately, this does still not close the gap to the Thorpe-Zwick distance oracles, but we believe that this is a very important and very hard question. I will get back to it at the very end. Okay, this is our main result. Let me further talk about two of our side results before I get into the details. So the first side result concerns, again, distance oracles, but in a slightly different regime, where, say, you're interested in very precise approximations. So the stretch should be, say, 2 or 3. If you're willing to spend more time in the pre-processing phase. So what's known in this regime? Well, first of all, if you're interested in stretch 3, you can just pick the Thorpe-Zwick distance oracles again, right? For k equals to 2, 2k minus 1 is exactly 3, so the stretch becomes 3, and the pre-processing time is O of m times root n. For stretch 2, you cannot immediately apply Thorpe-Zwick distance oracles, but there has been some work on this, first by Chechik and Zhang, and then with improvements by Dori, Forster, Nazari, and DeVos, who proved that for stretch 2, you can actually achieve a pre-processing time of m times n to the 2/3. Again, all these pre-processing times have constant query time. Okay, so what's known in terms of the lower bounds? It turns out that actually in 2012, Petrashko, Roditi, and Thorpe, they already proved that both of these results for stretch 2 and 3 are essentially optimal. So under some conjecture about the space complexity of set intersection, they prove that stretch 3 minus epsilon requires time m to the 3 over 2 plus, well, some function of epsilon. By the way, this lower bound only holds for sparse graphs, so you might think of a regime where m is equal to n. And this proves that, well, the algorithm from the left is optimal in the following sense. If you're willing to, if you insist on improving the stretch from 3 to 3 minus epsilon, you have to spend more running time, more pre-processing time. Similarly, the stretch 2k is optimal in the sense that it requires time m to the 4 over 3 in sparse graphs. Now, well, this result is very nice, and it's also very strong in the sense that it proves a space lower bound against these distance oracles, even in the pre-processing phase. Our result is nevertheless that we give the same lower bounds conditioned on a much more popular and possibly believable hypothesis, namely the threesome conjecture. Actually, we don't view this as a main result, we view this as a side result, but we view it also as evidence that our method, our lower bound method, might be tight, because it actually does achieve tight bounds in the small stretch regime. And there is another regime in which our lower bound techniques achieve tight results, which is in the case of listing 4 cycles. So let me introduce the problem briefly. Actually, first of all, let me introduce the 4-cycle detection problem. Here again, you're given an undirected graph. The task is to check whether it contains a 4-cycle. Okay, for instance, this one is a 4-cycle. And it is known since quite some time that actually you can solve the problem in either n squared or m to the 4/3 time by a very elementary algorithm, actually. And it is a big open question whether there is a matching lower bound based on like one of the popular conjectures. There are some non-tight lower bounds, but none of them match this under a believable conjecture. However, in the 4-cycle listing problem, you're not only supposed to check whether the graph contains a 4-cycle, but you're supposed to list all of them. let's say there are t many, then your output consists of a list of size t. And there is a very similar looking upper bound of the form n squared or m to the 4/3 plus t, which is also developed by Jining Xu and also by Amir, Abboud, Serikuri, Uri Leibowitz, and Ron Zafir. And well, one of our side results is also that we prove a conditional lower bound against this listing problem. So this algorithm is asymptotically tight. Okay. That's it for the introduction. Let me get to the technical part. And let me remind you that this is work on fine-grained complexity theory. So what we will do is we will start from a plausible assumption, in this case, the three-sum conjecture. And we will develop a series of reductions that ultimately reduce three-sum to our favorite problem, and which would then imply that if there is a faster algorithm for our favorite problem, in this case, distance oracles, you could solve three-sum faster, which we seriously doubt. So this is the web of reductions before our work. Let's go through it very, very carefully. First of all, the three-sum problem. It's very simple. You're given a set of integers, say it contains n many. The task is to check whether it contains solution to the equation a plus b plus c is equal to 0. It's conjectured that this takes quadratic time, and well, there is a simple algorithm matching this, namely guess a and b, c is uniquely determined. Now this very famous problem can actually be reduced to a less famous problem. It's called the all edges triangle problem, but it's very, very convenient to work with. So the problem is you're given a graph. Let's suppose for simplicity that it's root n regular. And the task is to decide whether for each edge, whether it's part in a triangle. Okay, so the output consists of not just one bit, but one bit for each edge, whether that edge is part of a triangle. And you conjecture that this problem can also be solved in quadratic time. And well, assuming the three-sum conjecture, you can prove that it requires time n to the 2 minus little of 1 to solve. Okay, this reduction is actually well known. It's originally to Petrashku, but then it was improved by Kohelovich, Petty, and Porat. And this problem is also very nice because there is another very famous problem, namely the APSP problem, which reduces to all edges triangle. It's proven by Vasilevska, Williams, and Xu. Okay, so starting from this, in the predecessor paper, what happened was that the authors, they took this all edges triangle problem, they transformed it into a very similar problem, which I call random-like all edges triangle here. And then they reduced random-like all edges triangle to the distance oracles. Now, the crucial step here really is the reduction from all edges triangle to random-like all edges triangle, which is by a technique they call short cycle removal. So what do I mean by random-like all edges triangle? Well, it's the same problem, but in some sense, the graph feels more random-like. And very specifically, that means that it contains only few k-cycles, namely roughly as many as a as a truly random graph would contain. So they could prove that actually this problem reduces to a graph with at most n to the k over 2 plus this constant many k-cycles. And well, as a consequence, you also derive some lower bounds for distance oracles. Unfortunately, both of these steps are not tight, which is why I've indicated them by these dashed arrows. So they suffice to prove the right order of magnitude of f, but they do not suffice to give precise bounds up to the constant. So this is where our work starts, and we augment the picture as follows. We add a new box to the picture, a new problem, which I will call random-like three-sum. And we will do this kind of structure versus randomness dichotomy not on the triangle problem, but we will instead do it on the three-sum problem. Okay, so we start from three-sum. We apply some kind of reduction, which we call the energy reduction, to make three-sum look more random-like. Then we follow a very similar reduction from random-like three-sum to random-like all edges triangle. And we use the reduction from random-like all edges triangle to distance oracles. Actually, we will improve it a little bit in order to make the constants match nicely. Okay, and from the very same problem, random-like all edges triangle. By the way, I should mention before this random-like all edges triangle had n to the k over 2 plus this constant many k cycles. the crucial step, the crucial improvement really is that we get rid of this constant and we get exactly as many case cycles as there would be in a random graph. Right, and from this you can also derive our corollaries for listing 4 cycles and for distance articles with small stretch between 2 and 3. Now, unfortunately, this talk is supposed to be 25 minutes, so I don't have enough time to talk about all these steps. Let me instead just focus on the first one. But actually, before, I should explain to you what I mean by being random-like. So let me start by a background on additive combinatorics. So throughout, I will use these pictures to just denote a set, where a bar means that I have included the respective element, and well, an empty bar means I have excluded it. They're more or less just for visualization purposes. You don't have to worry about that. Okay, here's the first very important definition. If A is a set of integers, then consider the set denoted A plus A. It's called the sum set of A, which consists of all pairwise sums of the form A plus B, where A and B are from A. Now, it turns out that the size of the sum set, A plus A, is actually a very crude measure of how structured versus how random a set is. Let me give you an example. Here I'm depicting 3 kinds of sets. At the 2 extremes, at the left, there is a random set, just drawn uniformly from some universe. And on the right-hand side, there is some very structured set. Think about an interval or an arithmetic progression. In the middle, it's half-half. Okay, well, so let's see, how does the size of the sum set behave in these cases? Well, the left-hand side, for a purely random set over a sufficiently large universe, you would expect that the pairwise sums A plus B are all pairwise distinct. So it follows that the size of the sum set A plus A is actually quadratic in the original set size. On the other hand, suppose you have an interval, all the numbers from 1 to n, say. Well, if you consider the sum set of that interval with itself, it will just be all the numbers between 1 and roughly 2n. Okay, so actually the size of the sum set is comparable to linearly in the original set size, which is quite different, right? So what happens in the intermediate case? Well, if you have a set which is half random and half an interval, what will happen is just that the random half will dominate the set size. Like whenever you pick 2 elements A and B from the random half, they will generate roughly quadratically many sums. So even for the half random, half interval case, the size of the sum set is roughly quadratic. There is another measure of randomness, though, which is more fine-tuned, which we call the additive energy. So it's defined as the number of solutions to the equation A plus B is equal to C plus D. Let me give you a feeling for this. I claim that it ranges from A squared for very random sets to A cubed for very structured sets. Right? So if you, again, consider a random set over a sufficiently large universe, we will not expect any non-trivial solution to this equation. But there are, well, A squared, roughly A squared, trivial solutions to this equation, namely taking A equals to C and B equals to D. So the additive energy will be roughly quadratic in this extreme case. On the other hand, if you consider an interval, it will generate cubically many solutions to this equation because you can pick A, B, and C more or less freely, and, well, D is determined. And the nice thing about the additive energy is also that in this intermediate regime, where you have half random and half interval, it will be large already. It will indicate that this set is very structured because it contains a very structured subset. And now there's this amazing result from additive combinatorics from the 90s, the Balog-Semiretic hours, or for short, BSG theorem, which states that if your set has very, very high additive energy, then it must contain a subset which satisfies 2 properties. First of all, the subset is decently large. And second, this subset satisfies that the sum set with itself is very, very small. So it's a very, very structured set. Think again about an interval and arithmetic progression. Okay, well, let me give you an example, namely exactly this intermediate case, in which case we know that the additive energy is very large. So there should be a subset, in this case, the subset indicated by the red bars, which has a very small sum set with itself. Should be, in this case, an arithmetic progression. Okay, and turns out that by Charlie Levenstein, it's already also known that you can find the set A prime very efficiently, say in randomized time, well, A to the 1.01 in the size of A. By the way, I have instantiated this theorem with constant that will work for our proof. Obviously, it's much more general, but for the purpose of this talk, we will not think about this general variant, rather about exactly these weird constants. They don't matter too much. Okay, so now that you know this on this background additive combinatorics, we have understood what we mean by A being random-like. So actually, in this random-like threesome, what we mean is that the additive energy of A is roughly A squared, which means that A really is super structured. It does not contain any structured part, super random. It does not contain any structured subsets in some sense. Okay, so let me talk about the energy reduction, and unfortunately then I don't have much more time. So what is our goal? We would like to reduce from an unconstrained threesome instance to a threesome instance with additive energy comparable to A squared. And we will achieve this goal in two steps. Well, we will first reduce an unconstrained threesome instance to one with energy less than A to the 2.99999. And then we will take that instance and reduce it further to reduce the energy to roughly quadratic. Okay? Let me put the goal one on the left side and goal two on the right side of it. Okay, so for goal one, this is the reduction. Don't worry, it's actually not that complicated. It does exactly what you would expect it to do. You take your set A, your threesome instance, and well, as long as your additive energy is too big, we just apply the BSG theorem, which says that there is some set A prime which is large and structured. Okay, we apply the BSG theorem, we find the set A prime, and our goal is to remove it. Because after we remove it, we have essentially removed structure from the instance. So after removing it and after repeating this step a couple of times, we will be left with an instance which has much smaller additive energy. But well, this is still a threesome instance. We cannot just remove parts of the threesome instance without violating the condition that there might be a solution in this set. So actually what we have to do is we first have to solve this threesome instance, by which I actually mean now a tripartite threesome instance, where the goal is to select one element from A prime, another one from the whole set A, and another one from the whole set A. If you find a threesome solution in this way, we just return yes. Okay. Now it seems like that didn't really make any progress here because, well, really I have reduced the energy of threesome at the cost of solving several threesome instances, but these threesome instances are very nice and structured. In particular, well, the sum set of A prime with itself is very small, so it's quite a technical challenge, but what we prove is that any threesome instance, A, B, C, for which the sum set of A with itself is very small, can actually be solved in subquadratic time. This does not suffer from the threesome conjecture. It can be solved in subquadratic time because it is so structured. So this involves a lot of more additive combinatorics. It also involves sparse convolutions. So I don't have time to cover that here. Let me instead go to goal two. So why was this helpful in the first place? With all this build up on additive combinatorics, all we've managed to do is reduce the energy from A cubed to something like A to the 2.99999. Is this really helpful? And the answer is yes, because as it turns out, there is a nice way of amplifying this improvement in the following way. Let me first introduce a very sketchy what I mean by linear hashing. By linear hashing, I mean a hash function which satisfies this equation. Whenever you have h of x plus h of y, this is also equal to the hash value of h of x plus y in a very idealistic setting. Don't worry too much about the details here. So it's known that there are many nice linear hash functions or something like almost linear hash functions. So the reduction does the following. We sample a linear hash function from our universe, from the universe of the threesome instance, to some number m of buckets. Then we iterate over each pair of buckets, x, y, and we construct the threesome instance, the sub-instance of our given one, which I denote by a, x, y, and it's just a subset of our original instance for which the hash values are restricted to either x or y or minus x plus y. Now, it might seem very non-obvious at this point, but actually in this way, we do preserve every three-sum solution. And you can check it as follows. Suppose there is a three-sum solution, a plus b plus c is equal to 0. Well, then pick x to be the hash value of a, y to be the hash value of b. And as it turns out, well, minus x plus y will just be the hash value of minus c. So indeed, we have satisfied that the hash values of a, b, and c are exactly part of the set. So we have preserved that a, b, and c are part of the set a, x, y. So this reduction is correct in the sense that one of the outputs, one of the sets that we construct, does contain an original three-sum solution. What we will analyze instead here is, well, how does the energy of these instances behave? Well, first, how does the size of these instances behave? Well, we have essentially subsampled our instance with rate roughly 1 over m, because we only considered like a constant number of buckets out of m many. Okay, so the expected size of each instance is roughly a by m. And well, the expected energy, it scales differently, right? Because remember that the additive energy was the solution to this equation. And for each solution of this equation, what's the probability that you included into our instances here? Okay, so well, for each A, B, C, and D, the probability that we include is roughly 1 over m. So you would expect maybe that each solution is only included with 1 over m to the 4. But well, recall that actually there is this dependence. So since we consider a linear hash function, after you fix the hash values of A, B, and C, also the hash value of D is uniquely determined. Okay, so actually we only get like the best we could hope for is like a 3-wise independence guarantee, which would give you like the energy by m cubed term. So okay, we can bound the energy of the set by size of A divided by m cubed. Energy of A divided by m cubed, which is A to the 2.999 divided by m cubed. Okay, so now it's quite magically, but if you pick the parameter m to be something like A to the 0.9999, actually the size of the set becomes, well, something very small, A to the 0.0001, whereas the additive energy becomes smaller in comparison. If you just calculate this expression here, it turns out that this is just A to the 0.0002. Now, if you compare these two expressions, indeed, the additive energy is quadratic in the set size. So what we've done is we really have reduced our one three-sum instance to several three-sum instances, all of which have quadratic additive energy. There is quite a serious challenge, though, challenge 2. Namely, I have assumed here that our hash function is 3-wise independent. And this was necessary to, well, make the expected bound of the energy work. So we are asking for a function which is linear and 3-wise independent. And as it turns out, unfortunately, these functions do not exist. And there's a very good reason why they do not exist. However, there is also a way to circumvent this issue. So to work with, well, a function which is sufficiently linear and sufficiently 3-wise independent at the end. Okay, that's all about the technical details. Let me very quickly wrap up. So yeah, the main open question after all this, it really is, what is the true complexity of distance oracles? So yeah, coming back to the question I posed in the beginning, what is the best stretch f of k we can achieve in the Thorpe-Zwick time? So with preprocessing time, order of m times n to the 1 over k, and almost constant query time. Now, after our work, essentially there are only 2 plausible outcomes. Well, either you improve the Thorpe-Zwick upper bounds, which would lead to f of k being just equal to k up to lower order factors, okay? Lower order terms. So this would prove that our lower bound is actually tight. Or, well, there could be better lower bounds. It is, in principle, conceivable that our lower bounds could be improved up to 2k, and it would really be amazing to settle this question in the end. Also, very quickly, I would find it personally very exciting if we find even more applications of additive combinatorics and algorithm design and complexity. Okay, that's it. Thanks for listening.